Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last time, where we were editing the parameters of the motor using the no-load test. So we had started off with the no-load test and we had extended the no-load test from the basic ratings which we had said every manufacturer provides. Now in this lecture we are going to continue and we will start with the blocked rotor test. So as before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length lectures, full-length courses, which you can access on several MOOC websites, and you can access this through my website, which is pythonpowerelectronics.com. So this website, which is pythonpowerelectronics.com, is the home page of this project, Python Power Electronics. So to know about the courses, please do check it out. There are several links here. But to check out the courses that are available, you just have to click on this button, Learn. So this takes you to the list of courses. So as of now, I have 5 courses. I will be creating soon, but not right now. The very first course I have is Simulating Power Electronic Circuits using Python. And in this, I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and this course talks about how you can use Python and specifically the Python packages like SciPy and Signal within SciPy to design and analyze filters, especially for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components like inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages like the Python control package to analyze and design controllers for power electronic applications. And specifically, I've chosen the case of a single phase converter connected to a single phase grid. And the last course I have is Why Specialize in Power Electronics, and this is more of a motivational course. It is a free course, and this course is to talk about the challenges and opportunities available in power electronics, and this is targeted towards either junior undergraduate students or even high school students who are yet to choose their specializations or even their engineering domains. So all these courses are available on 2 MOOC platforms. One is Udemy and the other is Decibel Labs. The buttons here can be used to click and access the course. The link for this page is provided in the description of this video. So if you're interested, please do check out the description. So with this, let me return back to my lecture. So as I said before, let's go back to the Excel sheet. So this was the very first Excel sheet which I drew, which contains the equivalent circuit of the single phase induction motor. Now, and with this I had gone through several descriptions where I had said that these are the different parameters and this is the significance of those parameters, and we can use the no load test and the blocked rotor test to calculate the different parameters. So here let's continue. We had already used the no load test, and as I said, the no load test simply means that we leave the rotor of the motor in the unloaded condition, so which means that the only load which is on the motor is the inertia of the rotor itself, and we apply the rated voltage to the stator. Now in the blocked rotor test, we are going to do exactly the opposite. In the blocked rotor test, we block the rotor. So we physically clamp the rotor so that it cannot move, and then we apply a very low voltage to the stator such that a rated current flows in the stator. Right? Now this test is analogous to the short circuit test in a transformer, and in that case, in the short circuit of a transformer, we short circuit one winding of a transformer and apply a low voltage to the other winding until the rated current flows in that winding. So these tests are very analogous. So in a blocked rotor test, because the rotor is blocked, physically blocked and cannot rotate, the rotor speed, which is Nr, is 0. So this slip, which is defined as the difference between the synchronous speed, the rotor speed, and divided by the synchronous speed, because this rotor speed is 0, because the rotor is blocked, the slip is 1. And therefore this term reduces to simple RR dash. which means that the rotor circuit is simply an inductance and a resistance combination. Now this inductance and resistance is not very large, and therefore you could say that approximately this rotor is almost a short circuit. Right? And that's how the analogy between short circuit test of a transformer and block rotor test of an induction motor can be made. So now that we are here, if this slip S is equal to 1, in that case we need a very low voltage applied to the stator such that a rated current flows in the stator. This is extremely important. When you do a block rotor test in the laboratory, after you block the rotor, you must very gradually apply a voltage to the stator, right? Because remember, if it is blocked, it's almost a short circuit. If you apply a very large voltage, you'll burn the motor. So therefore, very gradually we increase the voltage until a rated current flows in the stator. Now once a rated current flows in the stator, the ohmic losses that are falling across the stator, or rather the ohmic losses in the stator and the ohmic losses in the rotor, will be equal to the ohmic losses when the rotor is fully loaded. Why? Because the current flowing in the stator is equal to the rated current. So this way we can use the losses measured. So we can measure the total power loss that this stator at the stator point, and this total power loss is the total ohmic loss of the stator and the rotor, right? And at the same time, the voltage drops across the resistor and the leakage reactance, as well as the rotor inductance and the rotor resistance, will be equal to the drops when it is fully loaded. So this is how we calculate these parameters. At the same time, because the voltage is low, the magnetic field in the stator is negligible. Because remember, the magnetic field is directly proportional to the voltage applied. And if the voltage applied is negligible, in that case the magnetic field is negligible, and therefore this parallel path can be considered to be open circuited. So we can neglect these two branches, right? We can neglect these two branches and consider it to be a single loop, which is this outer loop. And as I said, this is what we are going to do here. So now that this basic recap has been done, let's go and start coding this. So let me go over to my editor. Let me leave some space. Let's have the no load test for comparison, and let's start writing. So blocked rotor test. Here in the blocked rotor test, the total losses, right? Let's go back to the editor. You see here that RR dash is very small, and of course these things we've already discussed. The total power loss is equal to the total ohmic loss and the total rotor loss, right? Now we can calculate the total impedance of this path. So we can calculate the total impedance of this path using this very simple formula. That is, it is the sum of the square of the resistance, stator resistance, stator leakage inductance, stator rotor inductance, and the rotor resistance, or rather the reactance is not the rotor inductance, right? And as you can see, we can make a few approximations. We can say that the rotor leakage, or rather the stator leakage reactance, is equal to the rotor reactance. I don't know, I'm twisting my tongue here, but yeah, so we can equate these two. What is however important is we cannot equate the stator resistance with the rotor resistance. This is not something that we can do. Alright, to calculate the stator resistance, and the reason is because the stator winding is a very different kind of winding as opposed to the rotor, which is in our case, of course the rotor also can be a winding, but for most cases, like in the case of squirrel cage induction motor, the rotor just consists of bars, rotor bars that are short circuited on either end. Therefore you cannot compare RR dash with RS directly. You cannot equate these two, right? So this approximation is not valid and you should not try to do it. So therefore, to calculate RS, we can use this formula, and we can say that when the rated current is flowing in the stator, 0.5% of the rated voltage will drop across this stator resistance, right? So which means this RS is a 0.5% is 0.5% or 0.005 per unit, and this is a fairly reasonable approximation. So this is the approximation that we will start with. So let's get started here. Let's say we've already calculated I rated. So if you go up here, we say we've calculated I rated. So all we have to do is we have to say, let me write this comment, drop across stator resistance is 0.5%. It's important to say it's 0.5% because remember, almost everywhere we are considering around 1 to 3%. Anything more than 2 to 3% of drop in a motor will result in a very inefficient motor. So do not choose something like 5 or 10%, though sometimes people do. So it's very important that any voltage drop, whether it's across a stator resistance or across a leakage reactance, should not be more than 1 to 2% of the rated voltage. Right? So drop is 0.5%. So of course what this means is I rated multiplied by stator resistance. Let me call this RS. Let me just check if I've used it before. Let me do a search. No, I have not, so I can continue to use it. Or I can actually be more specific and I say R stator. That's better. Is equal to 0.005 multiplied by V rated, right? So quite obviously, we just have to take this to the other side, and this is our R stator. So we have now calculated one value, right? Of course, you could say that you don't need even a block rotor test to do this. This you can calculate all the way up here, and maybe that is actually a reasonable assumption because this has nothing to do with the block rotor test. We are making an assumption. So let's move it all the way up here, and let's even move this comment up here. So now that we have our stator, we can now start actually doing the block rotor test. So for example, what we say here is total losses is equal to stator loss plus rotor loss. Actually, let me be a little more specific here. The total losses are the stator ohmic losses plus the rotor ohmic losses, because remember, in a block rotor test, core losses are negligible. Core, let me put magnetic losses are negligible because there is negligible magnetic field. So what this means is, if I have a block rotor test, just like I had P no load test, this block rotor test will be equal to I rated squared multiplied by R stator plus I rated squared multiplied by R rotor. Now here we need to make a difference that in the actual calculation, everything is referred to the stator. This entire equivalent circuit is referred to the stator, right? So everywhere there is an RR dash, there is an LR dash. So if we are referring to any parameter here, it is important to remember these are all parameters of the rotor referred to the stator. These are not actual rotor parameters. But let us not put things like dash and things like that, because then Python will complain. If you're very, very particular about it, you can put something like a referred at the end. Like dash R just means that these are referred parameters. Let me skip it all together because I don't really need it. We can calculate everything with just referred parameters. So now that we have this, quite obviously, what is this block rotor test? Now, in the case of a no load test, we took the no load losses to be around 1 to 3% of the rated input power, right? And this was a fairly reasonable assumption because the core losses, which are the eddy current losses and the hysteresis losses, will not be more than 1 to 3% of the rated input, right? However, the ohmic losses can be significant, right? A machine, when it is at rated efficiency, it will have an efficiency of around 85% at maximum output power. Now what that means is that you have around 15% of losses in your machine, right? So therefore we have to take into account the fact that the blocked rotor power is going to be much larger than the no load losses. Now you can choose whatever you want, okay, because like I said, machines come with several specifications and it is totally up to you. You can choose the losses to be 10%, 12%, 8%. If it's a very efficient machine that you're trying to simulate, you can even choose 5 or 7, 5 or 8%, but that's a very efficient machine. If you're choosing a really lossy machine, you can choose even up to 20%, right? 20-25%. More than that, there's something really wrong with the machine, right? So what I'm going to do, I'm going to choose 0.15 because that's what I chose here. So I have 15% losses, and this is equal to, what was the value that I gave? P in rated, sorry. So this is P in rated. So therefore, let me write a comment here saying that the blocked rotor power, and let me say losses, is 15% of the rated input power. Let me just collapse this so that I have more space. This is better. So this is what we have, right? This is an assumption. If you are actually performing the blocked rotor test in a laboratory, you can measure this. You can measure this using a wattmeter or using a multimeter or using an oscilloscope or using any other kind of meter that measures power. But this is something you can measure if you're physically performing the test, just like you can measure the no load power losses. So what this means is we can calculate using this. All we have to do is take this to this side and bring this here. Actually, let me copy this so that we have this for reference so that I know how I got it, and let me just put a comment here. And of course, once you have this, it's a simple arithmetic. And this is our rotor. So our rotor is this simple calculation. This is assumed. This is known through calculation using the rated manufacturer specification and a few assumptions. This is calculated. We also calculated our stator. All that means is using all these values, we can calculate the R rotor, right? So therefore, this value is now known. So we are down. So one down, more to go. So which means we have calculated RS, we have calculated RR dash. Now what is remaining is the stator leakage reactance or inductance, reactance, however you want to say this, and the rotor leakage reactance. Now we have assumed these to be equal, right? And this is usually a fair assumption because remember we are talking about leakage. Leakage means this is the amount of magnetic flux that is leaking out into the air and not linking with the rotor. So for example, when we talk about stator leakage inductance, this means that the current that is flowing through the stator coil is producing a certain amount of flux that is not associated with the rotor. This is not crossing the air gap and reaching the rotor. It is just getting leaked into the air or is just sitting in the air somewhere, right? This is not doing anything useful. And the same goes for the rotor as well. Rotor leakage reactance is merely that leakage reactance which, when the current flows through the rotor, the flux produced does not associate back with the stator. So this is what it means. And this leakage is usually, it is fair to assume that they are the same. Alright, because whatever it is, any magnetic system will have fairly the same amount of leakage, right? Unless you really want to go into details, this is usually a fair assumption. So that means, actually let's come back here, we can use this, calculate this approximation. So first let's calculate Z series. So if we come out here, we can say series impedance, and let's say Z series, and let's put a block at the end so that I know what I'm calculating. And this Z series, quite obviously, is equal to this value, but it is equal to the rated voltage divided by the rated current, right? This IS is the stator current, which in block rotor test is equal to the rated current. So this means it is V rated divided by I rated, right? And these have already been calculated. This is a specification, this is a calculation already done before. Now the next calculation is going to be a little interesting because this is a square term, right? Do not forget the square root. If you want to calculate the impedance with respect to the resistance and reactance, you have to take the square root of the sum of the squares. So therefore, we need to expand this so that we can just get one full equation, right? Now, all I'm going to do is write this entire equation and then pick out this one part that is remaining, right? So what this means, let's go and start writing, is R stator multiplied by R stator plus R rotor multiplied by R rotor, right? These are the two resistances, and there will be these two terms which corresponding to the leakage reactance of the stator and the rotor reactance, right? Now, since we are assuming them to be the same, let's equate them and put just one variable. So what I'm going to say is this is equal to X series blocked, and let's just put this. So let me put actually an X2 so that I know that this is a square term, right? Because this is the unknown, everything else is known. So all I have to do, let me do a little comment here, copy this, and I just have to bring this here. Can't seem to grab this. Right? So this is my equation. So all I'm doing is just taking this to one side, or rather this remains here, and taking this entire term to this side, right? Simple arithmetic. Now that I have this, right, I can say X series blocked is equal, actually not this, it is X series blocked because I am now creating a new one. This is a square term. Now this X series blocked is the square root. So all I have to do is say math.square root and X2 series blocked. So this is the reactance term. And this reactance term is equal to both reactances, which are the stator leakage reactance and the rotor leakage reactance. So therefore, all I have to do is I have to say stator leakage reactance is equal to rotor reactance is equal to X series blocked, right? And therefore this obviously means that LLS, or let me call this L stator, actually it's just, I will have large terms, but it's better to be explicit rather than write something very small and not know what it is. So L stator reactance leakage is equal to L series blocked divided by 2 into math.py into f rated, right? That is basically 2 pi f. So 2 pi fl is equal to x series blocked, and all I have to do is copy this, and I just have to say L rotor leakage reactance is equal to the same x series blocked divided by 2 pi f, right? So with this, let's go back and have a look if we missed anything. We have now the stator leakage, the stator resistance, we have the rotor resistance, we have the leakage reactance, the leakage inductance of the stator, and we have the inductance of the rotor. We have already calculated RC and LM. Therefore, starting, if we consider the motor, everything to the right of this line, we have all these parameters, right? So using the no load test and the block rotor test, we have calculated every parameter of the induction motor. So let me go back here and let me save this. So with this, we now have an equivalent circuit of an induction motor which we can use to simulate the induction motor. Now in the next lecture, I won't go straight directly to the simulation, but rather I'm going to run this and print out all these values that we've calculated and try to figure out what these are, right? So this is what we're going to do in the next lecture. And let's do a little analysis of these values and what they actually mean physically with respect to their physical significance, because after all, this is a machine, a physical machine. So with this, I'm going to end this lecture. If you have any doubts about what I did, or you have any other comments, either please send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week, where we will analyze some of these parameters and what they actually mean with respect to a physical significance of this motor. So thank you so much for watching, and see you soon. Goodbye for now.